Hello everyone. This is Abilino Dawes, your instructor. Before proceeding to the topic on load flow, let us first review the nodal method of solving DC circuits. Okay, so let's define the terms here. Okay, first is a node. What is a node? A node is a connection point between two elements in a circuit. And the second is junction. Now, it is a connection point of three or more elements in a circuit. Now, in the circuit shown below, the nodes are A, which is a common point of, or the connection point of the battery, and R1. And another node is node C, which is a common point of connection point of R3 and R4. And then another is of course D, common point or connection point of R4 and R5. And the last is node F, which is the connection point of R6 and the battery. Now for the junctions, we have node junction B, because B is the connection point of R1, R2, and R3. And then the other junction is E, which is the common connection of R2, R5, and R6. So some books, do not make distinction between node and junction. They call junctions as nodes, hence the nodal method, applies to nodes and junctions. Now in the nodal method, all connection points are labeled as above. And then a reference node is chosen, from which the node voltages are measured. The current in each branch is obtained by dividing the voltage difference between the nodes by the resistance connected connecting them. Then a Kirchhoff's current law is applied to each node in terms of the node voltages. The results are a set of equations, which the node voltages as unknown, which are then solved simultaneously to obtain, the node, voltages. After the node voltages are solved, the current in each branch is determined by dividing the voltage difference of the nodes, by the resistance of, the branch. Now, we'll have an example to illustrate, the nodal method. In this example, we have to obtain the equations needed to determine the node voltages of the circuits below. So this is our circuit consisting of several resistors, and we have two batteries at both ends, and then we labeled the nodes and junctions as these. So we have here A, then B here as the connection point of R1, R3, and R2. We have C and D, and then E and F. No? So the battery R2, R4, R6, and battery B have common connections which we call as F. Now, we choose F as the reference node, no, as it has the lowest potential in the circuit, being connected to the minus terminals of the battery A and B. So our reference node in a circuit shall be taken as the lowest potential in the circuit. So by inspection, since F here is connected to the negative terminals of battery A and battery B, then we have here the lowest potential in the circuit. Now, for simplicity, the single subscript notation is used. Thus, instead of BAF, the voltage between A and F, we just call this as B sub A. And we have BBF, the voltage between B and F, we just call that as B sub B, and so on. As the node voltages are measured, okay, from the reference point. So using the subscript, single subscript, okay, notation, okay, we have chosen, okay, a reference node already, no, from which, okay, this node voltages shall be measured. Now further, we do not include B sub A and B sub E as unknowns. Now since we know that B sub A is the voltage between A and F, which is just, okay, the battery voltage E sub A. And similarly, okay, B sub E is the voltage between E and F, which is just the battery voltage E sub B. So the unknowns therefore are only B sub B, B sub C, and, okay, B sub D. Now, step 1. Okay, first we consider node B. Now, when considering node B, okay, so we have to assume, okay, that the potential at B is higher than the potential of the other nodes linked by the resistances connected to node B. No? So by this assumption, okay, the currents, okay, in the branches connected to node B flow outwardly from B. Okay, since we consider that current flows from higher potential, okay, to lowest or to lower potential. Thus, okay, applying a Kirchhoff's current law at its node B, we have this, no? So we are considering, okay, node B, and as we said, we are assuming that the potential at B, okay, will be greater than the neighboring nodes, okay, which are connected or which are linked to B through, okay, resistances. So for example, the neighboring nodes of B are A and C, no? And of course, we have here the reference node F. So we apply Kirchhoff's current law at node B. Okay, so now since we assume, okay, node B to be of higher potential anywhere, so from for the current in through R1 would be flowing from B to A. So the current direction here is from B to A. And in this branch, okay, the current direction is from B to C. And of course, on the other branch, okay, we have the current flowing, okay, from B to F this way. So all the currents are away from B. So when we apply Kirchhoff's current law, which says that in some form, that the summation of the current of a leaving a node would be equal to the summation of currents entering that node. So uh, for leaving currents, we have the current here through R1, which is, okay, the potential at B minus the potential at A divided by R1. And then for this, the current here would just be B sub B over R2 because, okay, we have uh, the voltage across R2 is just BBF. No? So we have only B sub B, okay, over R2. Now, the current here would be B sub B minus B sub C over R3 equal to 0. And at the right, no, it's equal to 0 because, okay, there is no entering current, okay, to node B. So that's why we have here 0. So simplifying, now we collect terms with B sub no, B sub A. So we have here B sub A minus over R1. And then for terms containing B sub B, we have here, okay, B sub B over R1, and then another B sub B over R2, and we have B sub B over R3, and then we factored out B sub B. And for terms containing B sub C, we have only this, so minus B sub C over R3, and this is equal to, okay, 0. Okay, so there is no voltage B sub D and B sub E because, okay, they are not linked to, okay, node B. So we have only B sub A, okay, B sub B, and B sub C in this, okay, equation. Okay, so now since we know that B sub A is just equal to, okay, E sub A, no, the battery voltage is sub A, and uh, okay, when we transfer this to the right, okay, it becomes, okay, positive. So we just have E sub A over R1. And then at the left side, we have this term, okay, 1 over R1 plus 1 over R2 plus 1 over R3 times B sub B, and then we have minus B sub C over R3. So this is our equation. So before proceeding to obtain the next equation of, okay, the node voltage, okay, we observe that the coefficient of the node voltage we are considering is the sum of the reciprocals of all the resistances connected to that node. So here we are considering node B, and the coefficient of voltage B sub B, okay, is the sum of the reciprocals of all the resistances connected to B. So we have here 1 over R1 plus 1 over R2 plus 1 over R3. Then for the adjacent nodes, okay, we subtract their voltages divided by their respective resistance connecting to B. So, for example, the neighboring node is C, so we have to subtract, okay, B sub C over R3. And lastly, at the right side of the equation, we write the voltage source, okay, divided by the resistance through which it is connected to B. So at the right side, we have your voltage source is sub A over R1. So we go to step 2. So the next node that we're going to consider is node C. Now this time, we will assume that the potential at node C is higher than its neighboring nodes. So again, okay, the potential of C is higher than B and higher than D also. These are the two neighboring nodes of, okay, C. So again, okay, the flow of current would be from C to B, okay, through R3, and then the other current here is, okay, from C to D through R5, and the current, okay, going to the reference node, okay, through R4. So uh, with this and using the observation that we had, okay, in arriving at, okay, the first equation, so we are considering, okay, node C in this case. So we write, okay, B sub C, and then the coefficient of B sub C would just be the sum of the reciprocals of all resistances connected to C. So we have 1 over R3, then 1 over R4 here, and then we have 1 over R5 as the coefficient of B sub C. And then for the neighboring nodes, where at the left we have B sub B, so we have to subtract, okay, B sub B over, okay, R3. And then at the right we have, okay, B sub D. Okay, and we divide B sub D by R5. So that's how we can write our equation directly. Now, since at the right there is no voltage, okay, source, so therefore it is equal to 0. Okay, so we have to note that C has two neighboring nodes, okay, B and D. Hence, we subtract, okay, their voltages divided by their respective resistances. And then at the right, of course, we have, okay, to write 0 because there is no voltage source, no, connected to the neighboring nodes. Okay, now, okay, for the next node, we have node D. So again, okay, by, okay, using our shortcut technique, okay, so we write first, okay, B sub D, and then we have to multiply B sub D by the sum of the reciprocals of resistances connected to D. So we have 1 over R5, then we have 1 over R6, and 1 over R7. And then due to the neighboring nodes, we subtract, okay, their voltages. So at the left of B, we have B sub C over R5. And then at the right, now, we have B sub E, which is actually the battery voltage now here. So at the right, therefore, we write, okay, the voltage source divided by, okay, R7. So this is our equation 3. So these are, okay, our equations. Equation 1, which is this, and this is our equation 2, and we have here equation 3. Now, given, okay, this having obtained, no, these node voltages, okay, it would be, okay, better to write them in matrix form, because it would look like, okay, simple, not to see. Okay, so, okay, if these are our, okay, node equations, then writing in matrix form, okay, so we write first, okay, the unknown, the voltage matrix, which are unknown here. You know, so our unknown voltages are B sub B, and then we have B sub C and B sub D. So, okay, this is the usual way of writing our unknown voltages. So we have to order it like this. No, if I use letters, so A, B, C, D. Okay, so this would be the sequence of our unknown voltages, okay, to be determined. And then, of course, okay, the coefficient of these known voltages are our, okay, matrix, no? So, for example, for equation 1, okay, our first unknown here is B sub B. So, we have here, okay, this one times B sub B. So, we have this term. And then, this one times B sub C. No? So, we have this. And then, we have no B sub D. Okay, in equation 1, so we have 0 times B sub D. Okay, and at the right, okay, we write the known, okay, values, okay, which are usually the voltages. Okay, so corresponding to equation 1, at the right we have E sub A over R1. No? E sub A is usually given, so you can consider this as known. Okay, now for the second equation, okay, it's now B sub C, now that we are following. So coefficient of B sub C is this term. Okay, and then for the neighboring nodes, we subtract, okay, the voltages. So corresponding to B sub B, so we have this, no? So our equation actually is, okay, minus B sub B over R3, which is this, and then plus this times B sub C for this term, and then minus 1 over R5 times B sub D, which is, okay, this one, and we equate this to 0 because there is no, okay, voltage source now connected to C. Okay, so for the third equation, well, we have here B sub C over R5. Okay, now we do not have, okay, B sub B. So it's, okay, 0 here, no, corresponding to B sub B. So we have 0 times B sub B. And then we have, for B sub C, we have minus B sub C over R5. Okay, so minus 1 over R5 times B sub C, and then plus this last term here, which is in terms of B sub D. So this one times this, and we equate this, okay, to E sub B over R7 to the right. So this is how okay, we write our set of node equations okay in matrix form. So okay, you have to take note that we have here the matrix okay of known voltages, and then of course we have here the coefficient okay matrix, and then at the right we have to write okay the uh, voltage sources divided by the resistances. Okay, so if the values of E sub A and E sub B and all resistances okay are given, then all the node voltages okay can be solved no? uh, either using okay the matrix equation, the matrix form, or you can solve the equations as they are no? Individual equations okay in whatever method okay you use which we learned from algebra. You can use either elimination method, substitution method, okay, and other methods to solve okay the unknowns, okay, which are the node voltages, okay, given the values of resistances and okay the values of the battery voltages. Now, if we use the conductance, which is defined as the reciprocal of R, no? Remembering in our DC circuit that conductance G is the reciprocal of our resistance. So, G is equal to 1 over R. So, the equations that we had, okay, can be written as, okay, G1 plus, G1 is 1 over R1, no? And 1 over R2 is G2, and G3 is 1 over R3, and so on. So in terms of conductances, okay, we have this okay set equations, and in matrix form, okay, we have okay this now with the same matrix for node voltages, and at the right side we have okay these terms here. Now instead of E sub A over R1, we now have G1 times E sub A, and we have G7 times E sub B. Okay, so uh, moving forward, okay, observe again that the right side of equation 1, okay, and equation 3 are actually currents. Now, G1 E sub A is current now because I is equal to E over R. Okay, and 1 over R is G. So, GE is actually current. So, this is current now. And this is also, okay, current. So, remembering Thevenin's theorem, okay, which says that a voltage source in series with a resistor, okay, can be converted into a current source in parallel with the resistor across the same terminals. So, this is it. No? So we have a voltage source in series with okay a resistor okay with respect to terminals okay B and this. No? Okay, we can convert this okay into Norton's equivalent okay circuit, which is a current source okay IA in parallel with okay this resistance R1 across the same terminals B and okay this is okay F now in our network okay which is the reference node no. So between B and F okay we have this current source okay parallel with R1, okay, where of course our IA is equal to E sub A over R1. So redrawing our circuit now at node B, so we have this no because node A is now disappears no because we have considered this as this one. So node A is already eliminated. So okay, we have only with this node B here left no. So this current IE is entering okay towards node B, and then of course when now we have here a voltage okay, between B and this reference, so the current through R1 will be going down. So we have this current, and we had R2, no, connected between B and the reference node F. So current also is going down, and then we have neighboring node C, okay, through R3. So the current, okay, is going from B to C, no? Because okay, when we consider B, okay, the potential at B is considered to be higher than the neighboring node, so current will be flowing, okay, from B to C and from B to the okay, reference node, while current IE here, okay, will be towards, okay, node B. So applying a Kirchhoff's current law at node B, okay, summation of currents leaving is equal to the summation of the currents, okay, entering. So at the left, we have, okay, the current here, which is B sub B over R1. And then this current here is B sub B over R2. And then the current here is B sub B minus B sub C over R3. And at the right, okay, we have summation of entering current. So we have IE entering, okay, node B. So we have here IE. So simplifying our equation here, collecting like terms with B sub B. So we have, okay, this term 1 over R1 plus 1 over R2 plus 1 over R3 times B sub B. Okay, and then we have, okay, neighboring node B sub C, okay, over R3, and this is equal to IA, or this is equal to G1 plus G2 plus G3 times B sub B minus, okay, G3 B sub C equal to IA. So you notice that we obtain, okay, the same equation, okay, after we have converted, okay, the voltage source, okay, in series with the resistance R1, okay, into Norton's equivalent, okay, circuit consisting of a current source, okay, which is towards the node, no, we're considering, and okay, parallel with the resistance, okay, R1. Okay, so that's the node voltage equations in matrix form, okay, in terms of the conductances, okay, is this one. Okay, so this is our, okay, a set of node voltages, okay, written in matrix form. So we have here IA, and of course we still have this node voltages, which are going to determine, and these are the coefficient matrix. No, so we notice here that at the right side, okay, we have currents, no, and we call them as, okay, current injections, okay, current injections, because as we have seen, okay, IA is, okay, towards node B, while uh, this is IB is, okay, towards B sub D, you know. So we have this as, okay, current injections, okay, coming from battery A and from battery B. So in general, okay, our node equations can be written as this. Now we have a set of, okay, node voltages, which is just called as, okay, B1, B2, B3, and so on. And then we have coefficient, okay, matrix, which we just call as, okay, G11, okay, G12, G13. No, and we have G21, G22, G23. On we have G31, G32 plus G33. So in other words, when we write this in expanded form, then we have here G1, okay, times B1, okay, plus G12 times B sub 2, and G13 times B sub 3 equal to I1. And similarly, for the second equation, we have G21 times V1, okay, plus G22 times V2, okay, plus G23 times V3 equal to I2. And lastly, we have G21 times V1, G32 times, okay, V2, and we have G33 times V3 equal to I3. Now, okay, now, this is a coefficient matrix in terms of conductances. Okay, we have elements that are equal to 0. So, in this case, for example, of the equation, or in the example that we are considering, this is G13, no? So G13 here is equal to 0. And also this one is G31, okay, and it is equal to 0. Now, we can observe that in matrix form, okay, our coefficient matrix is, okay, symmetrical. Okay. So, for the diagonal elements consisting of these, no, these are what we call as the diagonal elements, or in the general equation, we have diagonal elements, okay, G11, G22, G33, no, so these are, okay, different, no, values, but we notice that for the, okay, off diagonal elements, okay, they are symmetric now with respect to the diagonal. For example, this one, we have minus J3 here, and we have minus J3. So meaning, in this one is G12, and it is the same as G21. Okay, so, okay, so G12 is equal to G21, no? Okay, equal to G3. Okay, so this one G13 is also equal to G31, okay, equal to 0. And this one is G23, the same as G32. So these elements are symmetry. Okay, so that's one observation that we can get by writing our node equations in matrix form.